Imagine shaking a rope up and down. This produces a transverse wave, which is a type of wave that moves perpendicularly to the direction of its propagation. The wave speed depends on the tension of the rope. With greater tension, the wavelength increases. With less tension, the wavelength decreases. Now imagine if the rope is tied to a wall with a fixed end. The wave reflected from the wall will come back and interfere with the waves moving toward the wall. This is wave interference, where two waves interact and either constructively increase or deconstructively decrease amplitude. At certain frequencies, nodes will form where the interfering waves cancel out, and antinodes will form where the waves create larger amplitudes, producing standing waves. We can see that the amplitudes of the right traveling wave and left traveling wave combine to create the net amplitude of the standing wave. The concept of standing waves can be demonstrated using a string with one end attached to a mechanical wave driver that can vibrate with variable amplitude and frequency. On the other end, the string is fastened to a stand with a hooked mass attached. This will create tension in the string. We can control the frequency of the wave with this function generator. We'll start with the frequency at 0 and slowly increase the value. Eventually, we'll be able to see the fundamental frequency, the frequency which produces the longest standing wave, called the first harmonic. The fundamental frequency here is 35 Hz. As you continue to increase the frequency, the second harmonic appears. The nodes are visible at the points of the string where it does not move, one at each fixed end of the string as well as the center. The antinodes can be seen where the string moves with maximum amplitude. The frequency of the second harmonic is 70 Hz. Notice it is twice as big as the fundamental frequency. This is because there is a mathematical relationship between the wavelength of the wave that produces the pattern and the length of the medium in which the pattern is displayed. So we can expect then that the third harmonic to appear at 3 times the fundamental frequency, which would be 105 Hz, and so on and so forth. Now we can explore the same concept in a two-dimensional space using Chladni plates, where I place the same wave driver in the center of this aluminum plate. This means that the vibrations caused at the center of the plates will travel outward until they hit a change of medium and then bounce back. At certain frequencies, the waves traveling out and back will produce a standing wave, similar to what we observed earlier. We can visually observe the standing wave patterns using sand, as they collect in the nodal regions and form sharp, distinct lines. Like before, we'll start the frequency at 0 and slowly increase the value. Eventually, we'll be able to see the fundamental frequency and its associated pattern, which here is 193 Hz. As we continue to increase the frequency, we'll see the next harmonic and a new pattern created from the nodal regions. When you touch any of the nodal regions, the pattern is unaffected since the plate is unmoving in that certain location. But when you touch any of the antinodal regions, it will disrupt the pattern. The standing wave patterns are dependent not just on the frequency, but where the driver is located, or the type of material of the plate, or the fact that these edges are not fixed in place. Due to these various factors, the patterns you see for the third, fourth, and rest of its harmonics are unique.